I'm an MIT professor, but I work at Google, and that's a Google-owned computer, and that's why it always logs out, and I have to type in a password, because they don't trust me to just leave it open and have people spy on it. So there's a Google-owned computer, so it's probably spying on you right now. It's going to gathering data to use against you. Goldstone, that is the same guy as Goldstone Bosons. If you ever heard of Goldstone Bosons, if you're a physicist, that's the same guy that my friend Sam got in. Okay, so I wasn't exactly sure how to pitch this, so I think it's going to be inconsistent will be my approach. That I'll be too simple or too hard, and nothing in between. All right, so anyway, there's a quantum computer, and I think we are all challenged with the question of after we've built one, what do we do with it? We want to put in a lot of zeros at once to get stuff out to solve hard problems. So the question that really interests me, though, is, what do we really want to do with a quantum computer? I mean, I think, and I'm not really interested in proving, that quantum mechanics is true or something like that. I'm much more interested in asking, can we use quantum mechanics for computational advantage? Can it help us solve a problem that we couldn't otherwise solve? So I'm going to be really viewing this, my approach is really, I view myself as a quantum mechanic. I'm an engineer. I'm trying to use my real knowledge of quantum mechanics to advance computation. That's the position I was to adopt today. Okay? So it's in the service of computation. And so in this regard, let's just go over with the difference between a quantum computer and a conventional computer. So in a conventional computer, you input a string of bits, 0, 1, 1, 0, 1, 1, 0, something like that. And that's supposed to encode some kind of problem, or instance of a problem that you want the answer to. And then the quantum computer outputs a bunch of ones and zeros, which encodes the answer to the problem that you wish to know the answer to. Okay? So that's what the computer does. And of course, what goes on between the input and the output, that's what computer science is about. And in a quantum computer, you want to have an input, but instead of having zeros and ones, you have a spin down. So spin ups and spin downs. So we input a string of ups and downs, like an up here is 0 or 1, we input the string, and we turn the crank, and out comes the answer, which are a bunch of strings, which encode the solution. So this is quantum computing, that's fun. Okay? Everyone can see the difference? Good. All right, good. You're listening. But the point I wanted to make here is that I'm going to be interested in this talk in solving computational problems which are encoded by bit strings and which the answer is encoded as a bit string. There are many other uses of quantum computers you can imagine, like simulating physical systems, or let's say finding the ground state of a molecular system, or trying to model a physical system with another physical system. And I think these are absolutely interesting questions, but it's just not the subject of today's talk. Today I'm thinking much more in terms of conventional computation, input a string, output a string, and the input is probably a kind of representation of the instance of the problem, and the output is the answer. So there are lots of computers. Yeah. So let's move on, and I'm going to try to talk now. I am interested in what we might do with a near-term quantum computer. So I'd like to talk about a specific algorithm, which is for approximate optimization. So I'd like to talk about what that means, what's approximate optimization, and what might we be able to achieve with a quantum computer. So I'm going to be interested in combinatorial optimization. I assume a lot of you know what this is. I hope so. What this is about is this. I have always 10 bits, and I want you to think of that as a number like 100, or maybe in a near-term quantum computer 20, or 1,000. But n itself is not too big. But since n represents bits, those bits contain 2 big values. So that's 1,000, and that's 2,000 possible big values, and those are numbers which are beyond numbers of the characteristics. They're all about 2 to the 1,000 photons. So anyway, n is a good thing about it. And then because these combinatorial optimization problems, you have bits and clauses. And what a clause is a restriction on a subset of bits. So it looks at some of the bits and says for certain assignments it's true, and for certain assignments it's false. That's what a clause is. And then we can associate with an instance of a problem, sort of a cost function or an energy function, which if you look at a string, this C stands for Z1 through Zn. Each of these C's take 2 values. So this C takes 2 to the n possible values because I'm writing in bits. And each clause, if it satisfies it corresponds to the little output of 1 for this little function, and 0 if it does not. Okay? And the goal then is to find the Z that maximizes. We would like to find, the ultimate goal is to find the Z that maximizes this function. Now this problem of having clauses acting on subsets of bits and trying to find the maximum over all inputs of their cost function, this is the mother of all computer science problems. This is the hardest problem in some sense of computer science. If you had an algorithm that could visually do this for every substantiation of a problem, if you could always do this optimized, then you would be showing that P equals NP. In general, finding this maximum is just very, very hard. Now you might think the way I'm going to approach it is I'm best string is very, very challenging. But, sometimes, the best is the enemy of the good. And if you obsess too much about finding the best thing, you might miss a good solution. So I want to look at something else, which is to look for a string Z such that C of Z over the maximum is a sum big. And this is called an approximation ratio. So if you have a computer that outputs a string Z, where C of Z over C max is big, I mean, you can't be with 1. Obviously, 1 is the ultimate thing. But, good value, then you're not very happy. So we're going to talk about quantum algorithms and trying to maximize this ratio. We also, there's a lot to say about this, and get to later about, how hard is the problem really? And sometimes it's really very hard, and sometimes it's not so hard. And this is a big study in European computer science in the last 20 years, is understanding the boundaries of how difficult this is problem. To just get a good solution, not a good solution. So we're going to try to be more specific about that by example. So, I'm not going to talk about quantum algorithm, and this is a gate model. And I was hoping most of you know a little bit about quantum computing, what a unitary is, and have a basic idea of how this works. So the first thing I want to introduce is a unitary operator. This is acting on the Hilbert space spanned by n spins. So we have n spin-and-a-half particles. They span a 2D n-dimensional Hilbert space. So each, if I have a spin up in the z direction, I think of that as a 0. If I have a spin down in the z direction, I think of it as a 1. So there's a natural basis for this Hilbert space, which I guess is spin down, which corresponds to spin space, particle spin up and spin down. And this cost function, which I wrote on the other slide, I wish I put another slide in explaining that in this language, that cost function I'm thinking of as an operator acting on states, which corresponds to strings. So if I have a string, which is up, down, down, up, down, up, like that, then the cost function acting on it multiplies it by the value of C on that string. That's what I mean by this cost function when I'm thinking of it as an operator. I'm going to put a little hat on it. But notice, and now I would like to imagine I have this cost function, and I have some parameter gamma. And gamma is just an angle. It's a number between 0 and 2 pi. And I consider this operator, e to the minus I gamma c, which we can write as a product. So c was, remember that c on the previous page we saw was a sum? So I can write this as an exponential. So this operator, you can think of as a product of m operators, each of which acts only on the qubits associated with the clause C. Because remember I told you that clauses involve subsets of the bits. So if my clause involves, let's say, bits 1 and 7, then the associated operator here would only act on bits 1 and 7. So this is a product of local commuting operators. And the reason I'm emphasizing that is this is something we imagine we'll be able to build in a near-term quantum computer. Objects will be able to manage little gates which act on, let's say, 2 or 3 qubits. You may ask me, is it important that the qubits be lined up or laid out geometrically? Well, let's put that aside for now. Let's just imagine that I can build this. The other operator I want to think of is the sum of the sigma x's. The computer scientists like to call it sigma x. So there's an operator b, which you can just think of as it's just the sum of all the spins in the problem of the sigma x's. And then there's another operator, which I'm going to call u of d beta, using the same notation, which is e to the minus I beta b. And this, because b is a sum of commuting terms, can also be written as a product. J equals 1 to n, e to the minus I beta sj. You can think of this as performing on single spins rotations about the x direction. So this is each of these is a little 2x2 unitary transformation, which rotates each spin by around the x direction by an angle beta. Okay? And then I have a starting state, which is where I begin the algorithm. I'm giving you the ingredients of the algorithm. The starting state is the uniform superposition of all the possible string values. So there are 2 to the n strings here, because Z, remember, was Z1 to Zn. But even if I write it as the uniform superposition of everything in the Z direction, there's an easy way to achieve that, and that's to just line up your spins in the x direction. Because if your spins are lined up in the x direction, each spin is a uniform superposition of up and down. So the whole thing is a tensor product of up, down, with up, down, with up, down, with up, down, which is all possible combinations of up and down, which is also called the state S. So this is easy to construct in some kind of idealized world where people are building gate-model quantum computers. Okay? So now, for any integer p, although unless the p is small, I want to imagine that I have a bunch of gammas and a bunch of betas. So, let me do this. So in other words, I have gamma 1, gamma 2, gamma p, beta 1, beta p, and I just put an arrow 1 as a shorthand. And now I want to consider the following quantum state. It depends on the 2p angles, and I act on the state S with first the unitary operator with the C with the angle gamma 1, then the unitary operator with B with the angle beta 1, then I do with the 2, 3, 4. So there are 2p gates here, 2p unitaries, excuse me. Each of those can be decomposed into more fundamental units, and in fact the required circuit, oops, what happened? The required, I'm doing something wrong. I'm sorry. The required circuit depth here is at most MP plus P, because you can just figure that out. Okay. Now, what I want to do here is I want to build this quantum state with a quantum computer, and then I want to see what the expected value of the cost function is in that state. So 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 I have an object which depends on P and the angles gamma and beta, which is the expected value of the thing I want to optimize over gamma and beta. And so now let me define MP as the maximum I can get by varying gamma and beta of FP of gamma and beta. In other words, there are a set of angles of 2P angles. Don't think of P as too big. Think of P as, I'm going to talk about P with 1 in a minute. So there are going to be 2 angles. So think of P as not too big. And so so this is a function of just a bunch of angles. The reason they're angles is because these are integer valued operators, C and D. So when they're integer valued, the parameters, they wrap around. Integer value, the eigenvalues are integer. So if you exponentiate them with e to the I something, you can just have an angle up there because if you increase it by 2 pi, you just come back to where you are. So these are not, so these are just angles. And so there is a maximum I can get over these angles. And I call it MP. And note that MP is larger than or equal to MP minus 1. Why is that? Because if I look at MP minus 1, that is the maximum of this quantity where I have forced the last 2 angles to be 0. Because, you see, if I force the last 2 angles to be 0, I'm at the stage below. So MP is, so at level P minus 1, I'm doing a constrained optimization relative to level P. So that means the maximum can only be less than or equal to this. Okay, so that means that as I increase T, I can only make the thing bigger. I mean, maybe it won't increase, but I can only make it bigger. And then I can actually prove, but I'm not going to do this, that if we take the limit as P goes to infinity of MP, there are angles that achieve Cmax. But let's just leave that aside, because that means that if I can find angles which will achieve perfection. But it's not too interesting because this P this is the limit as P goes to infinity, and I'm not really interested in ever constructing a computer which requires an infinite number of gates. I mean, maybe I could as a whole class now, but I'm going to put that aside, but it's just worth noting. So this algorithm, well, I haven't said what the algorithm is. But let's think about what the algorithm is. So let's call it